Okay, so here we have AP Review 6 solutions, two problems, one involving a collision between an arrow and a pumpkin, and the other with a diver rotating from a platform. Okay, so the first one is an interesting problem. It's one question. You get a lot of information, so obviously got to read carefully, but basically we have three arrows that are identical. One bounces off the pumpkin, one embeds itself in a pumpkin, the other passes through the pumpkin. And they want to know how that will affect the angle that the pumpkin rotates up to here. And you have to write a paragraph explaining all the points, and obviously you want to get the right rankings. So the main, I think this is 7 points. The important thing to realize is the explanation more than anything, even if you get the right answer. Okay, so in terms of ranking, actually let me go back to that. I can do that right here. If one is the greatest, that's the one that's going to bounce, right? That's is 1. The one that embeds is 2, and the one that passes through is 3. So I believe that's only one of the 7 points. So how do we go about explaining that? Here are the key points, and I'm not going to write in paragraph form, but I'm going to do it in a bulleted form. Okay, it doesn't have to be exactly this, but it doesn't have to be necessarily in this form. You want to make some statement that we're going to use conservation of momentum. You don't have to write it in terms of the equation, excuse me. But you got to make clear that this is ultimately going to be solved using conservation momentum. Another point you need to make is that a bigger angle, okay, right, that's what we're trying to do, comes from a larger momentum of, the pumpkin, okay? So whichever situation transfers the most momentum to the pumpkin is the one that's going to go highest. Then it would lead to, how do we do this? Well, we want to make clear that the loss in momentum of the arrow, and again, I'm just doing this in equation form, but you can do this in a statement. So whatever amount the arrow loses momentum equals the gain of the pumpkin. Whoops. Okay, and that's really just a restatement of the law of conservation of momentum. So if you just make this statement, let's assume, I think that would take care of this statement. And then you still need to make it clear that the bigger angle gets the larger one. So now we have our blueprint. Whichever arrow had the greater change of momentum imparted the same change of momentum to the pumpkin, therefore it goes higher. So we take each one. So the one that bounced, let's just take the bounce. You'd make a statement about that. Why do we rank that first? Because delta P, right, is going to be, and again, I'm not quite sure how explicit you have to be. Take a look at the PDF, but you can, using, what did you say, delta P equals P initial, right, minus a negative P final. And we want to make clear that negative part because it bounced off. So that is going to give us a large delta P. Whoops. And you're basically making the same argument for the other one. So for the embed, which I believe, okay, right, your delta P of the arrow is simply going to be 0, right, minus P, right? Well, actually, it's not going to be 0 because I believe it swings a little bit, but it's going to be a small change. It's going to have a small velocity afterwards minus the initial one, so it's not going to be as big as this one. And the one that passes through, okay, you have to make some argument that the P prime of the arrow, after P prime of the arrow, that means after, is fairly large, is still high, something like that. Therefore, delta P of the arrow is low. Okay, so and then with those taken into account, then we have the evidence we need for the relative changes in the arrows, change of momentum. All right. Again, the PDF probably do a much better job than I just explained there, but that's the essence of it. Now let's go to the next problem involving the diver. Let me scroll down to that. So we have a diver, 3 parts, 3 positions. When they dive, do a tuck towards the top of the platform and then go into a pike. And there's 2 questions I want to ask here. So again, paragraph. Why the angular speed, okay, so that's omega, increases from here to here and then decreases from here to here. Your main arguments from here to here is going to be similar from here to here, but you just got to make sure you don't forget that part, because I would have done that. So how do we go about explaining that? What physics governs why the angular speed changes when we basically go from, so you got 2 things you can potentially look at. The actual shape, if you will, of the person, right? Here they're in a pike, tuck, pike, or their relative heights. Turns out one matters, the other doesn't. So what I hope you recognize in this one is it's the shape of the person that matters, whether they're stretched out or tucked into a smaller position, because that changes their moment of inertia, and we want you to relate that to angular momentum. This is not so much about gaining speed by falling. While that certainly helps, that really doesn't go towards how fast they're going to be spinning round and round. Okay, so again, I believe this is not 7 points, but it's around 5 points. What are the things we need to make? The points we need to make. First, and I mentioned this earlier, we have conservation of angular momentum. There's no external torques acting on the person as he or she changes their body shape. The gravity is the only force acting on them when they're in the air, and the gravity acts always through their center of mass or center of gravity, so there can't be any external torque. Okay, so you have sigma L equals sigma L prime. You want to then make some statement that angular momentum is calculated as I times omega. Okay, their moment of inertia times your angular speed. So there is the variable in question. You want to make some statement that when they're extended, or you don't have to use the word pike, but you can describe something along that, has a larger I, larger moment. To be safe, you could put Y as that, because the mass is extended, okay, from the pivot point, right, the axis of rotation, all right, something along those lines. Then you make the statement that if we have I omega equals I prime omega prime, then that means that omega prime is going to equal to the ratio of their moments. In other words, just show there's an inverse relationship between I and omega. A bigger moment is a smaller angular, and vice versa. So you don't have to, something like this, and then lead that towards, in case from going from 1 to 2, right, essentially I goes down, therefore omega goes up. That's from 1 to 2. And then make another statement from 2 to 3. You don't have to reiterate all this. It's the same argument. Okay, I goes up again as they go back in the pike. Therefore, omega goes down. All right, and then the second question asks, let's see, what happened to it? All right, how does the angular kinetic energy here compare to here? And again, you might be tempted to think in terms of conservation of energy, but they're more or less at the same height, so it's not so much going to change because of that, but it's actually a little simpler. It's just maybe not so obvious. Okay, and it's again angular momentum conservation. At number 1, we have, right, an I, how should I say, a big I, small omega, that's going to equal, at position 2, a small I and a big omega. So how does that translate to rotational kinetic energy? Well, rotational kinetic energy, so you need to make some statement that that's I omega squared. So you can make the argument either algebraically or in words that even though there is a proportional dropping of the for a proportional drop in moment of inertia, there's an increase in omega. They don't have the same effects because of the squared part. In other words, if we double omega while having I, right, that's conservation of angular momentum, you're going to get 4 times the kinetic energy. But when you do the reverse, you're not going to quite get that because of the squared part. So long story short, the omega has a bigger influence on kinetic energy than moment, where that's not the case for angular momentum. Okay, that's it for number 6.